Welcome to the Explainer. We hear about large language models all the time, but they're kind of a black box, right? Well, today we're going to pry that box open and take a look inside to see what's really going on.
I mean, you've definitely used one of these things. You type in a prompt, maybe ask it to write an email or a poem or even some code, and boom, a perfectly coherent response just appears.
And it's kind of spooky, right? It really feels like you're talking to a thinking machine, like there's some kind of consciousness on the other end that's actually getting what you're asking for. So what's really going on under the hood? Let's dive in, because the reality, well, it's both way simpler and honestly way more clever than you might think. This isn't magic, it's just a really, really cool process. All right, first things first, we gotta bust a big myth. These models do not write the whole response at once. Not even close. What it actually does is work in a loop, one word at a time. Seriously, it takes your prompt, and its only job is to predict the single most likely next piece of a word, which we call a token. Then, and this is the key part, it tacks that new token onto the end of the prompt and feeds that new, slightly longer prompt right back into itself to guess the next token. It just keeps repeating that, building the response piece by tiny piece. This whole process of using its own predictions to make the next prediction, that actually has a name in machine learning. It's called an autoregressive model. And trust me, this is the basic idea behind pretty much every text-generating AI you've ever interacted with. Okay, so we keep saying the model does this or that. But what is the model? What's inside this thing that's running the loop? Well, we can actually break it down into three main parts that work together, one after the other. Think of your prompt going on a little trip. It starts as regular text, gets translated into machine speak, goes through all the processing, and then gets translated back into text you can read. Let's follow that journey, step by step. The first stop is the tokenizer. You can think of it like the bouncer at a club. It takes your text and chops it up into these little pieces called tokens. Then it checks each token against its massive vocabulary, its guess list, and swaps it for a special code, a string of numbers we call an embedding. This embedding is like a numerical fingerprint for the word. It's how the model turns our language into math it can actually work with. Okay, so now we have our numbers. Where do they go? They get sent to the heart of the whole operation, a big stack of what are called transformer blocks. And when I say stack, I mean it. A model like Phi 3 Mini has 32 of these layers, one right on top of the other. This is where the real magic, all the heavy lifting and the deep thinking actually happens. All right, after that long journey through all 32 of those layers, the processed information finally reaches the last component, the language model head, or LM head. Its job is super important, but pretty straightforward. It looks at the final output and creates this huge list of scores, one for every single possible token in the entire vocabulary. And this is basically what that list looks like. It's just a giant probability game. So let's say your prompt is to start an email. The LM head might say, okay, there's a 40% chance the next word is dear, a 25% chance it's subject, and so on. And then the model just picks the one with the highest score. That's it. That becomes the next token, and the whole loop starts again. But hang on a second. How do those transformer blocks actually know what to do? How do they make such good predictions? Well, the secret sauce, the real genius of it all, is a concept called attention. And this quote is so cool because it's literally the title of the paper from 2017 that started this whole revolution. Attention is all you need. It's not just a clever title, it's pointing right at the key idea that changed everything. Okay, look at this sentence. The dog chased the squirrel because it was fast. The whole meaning of that sentence comes down to that one tiny word, it. Who was fast? The dog or the squirrel? Now, for us, that's obvious, but think about it from a computer's perspective, just looking at a string of numbers. How does it know? That's the exact problem the attention mechanism solves. It's designed to figure out the relationships between words, even if they're far apart in the text. So inside every single one of those transformer blocks, you've kind of got two parts working together. There's the feed-forward network, which is like the model's long-term memory. That's where it stores all the facts it learned during training, like the Shawshank is usually followed by redemption. But then you have the attention layer. That's the context part. It's what looks at the current prompt and helps the model figure out which words are important to pay attention to right now. So this is an amazing process. But think about it.
The model has to do all of this for every single word it generates, one by one. That would be insanely slow, right? So of course, engineers came up with a really clever trick to speed the whole thing up.
Okay, so instead of rereading the entire history of the conversation every single time it adds a new word, which would be super inefficient, the model uses a cache. It's called a KV cache. Basically, it stores the results of its past calculation so it doesn't have to do the same work over and over again. This way, it only has to focus on processing the newest token. It's just way smarter.
And this isn't a small improvement. We're talking about a massive difference. In one test, this simple caching trick made the whole process almost 5 times faster. This is the key. This is what makes it possible for you to get those fast, streaming responses that feel like a real conversation.
Okay, let's put it all together. Let's do a quick recap of that whole journey, from the moment you hit enter to the final word appearing on your screen. So it starts with your prompt getting chopped into tokens. Those tokens get turned into numbers and sent through that big stack of transformer blocks. Inside each block, the attention mechanism figures out the context, while the feed-forward networks apply all the stored knowledge. Then the LM head predicts the single most probable next token. That token gets added to the prompt, and the whole loop repeats, supercharged by that KV cache.
So, you see, it isn't really thinking in the way we do. It's an incredibly sophisticated pattern-matching machine, driven by logic and probability. But the thing to take away here is just how elegant that whole system is. And it leaves you with a pretty wild thought, doesn't it? When a machine gets this good at finding and repeating our patterns, what does it mean when those patterns become basically indistinguishable from our own?